current electricity, and electric circuits. Static electricity has its uses, but if we want to harness the energy of electrons to do continuous work, we need a constant flow of power. Static electricity only provides short bursts of electrical energy that cannot be used to power devices in our daily lives. If we could find a way to harness the energy of lightning and store it, there would be more than enough electrical energy to power anything we could imagine. However, we cannot, so we need to use other electrical energy sources to produce power for our day-to-day lives. Take the time to think of all the devices and appliances you use today before you got to school that use electricity, and list these devices here. Today we're talking about current electricity. This differs from static electricity that we discussed earlier. Current electricity is electric charge that flows from one place to another. And electrical energy is the energy that is provided by the flow of electrons. When these electrons are moving, they can do work. They can power our devices, they could run our lights, our computers. They can do so much because of their electrical energy. There are sources of electrical energy. Where do you get your electrical energy from? You can get it from voltaic cells. These are a source of energy that generate current by chemical reactions involving different metals or metal compounds separated by electrolytes. A D-cell battery or a AAA battery is a cell. When we connect more than one cell together, we create what is called a battery. 3 AAA batteries are 3 AAA cells connected together, and we call this a battery. If a cell can only be used once and you need to throw it out when it's done, then it's called a primary cell. If a cell can be used more than one and it can be recharged, it's called a secondary cell. Direct current and alternating current, DC and AC. Direct current is a battery. It provides energy and the electrons move in one direction. Alternating current, from power plants, electrons move back and forth through the wires. This is the type of electricity we get in our homes through outlets in our walls. And DC is from our portable electronic devices with batteries. How electric circuits work. Electric circuits are pathways for electrons to flow. We will be learning about electric circuits made up of one or more loops of electrons that electrons can flow through. There are 4 different parts of a circuit. The first is the source of electrical power, such as a battery or a household wall outlet. The second is a conductor. In order to have an electric circuit in which electrons flow, we need a conductor. We need a path. These are wires or printed etches on a circuit board. Next, we need a load. What is the point of our electric circuit? This is the device that needs electrical power to operate, such as a lamp, a motor, or a speaker. And finally, you need a control, an ability to turn it on or off with a switch. We use circuit diagrams to represent the electric circuits around us. In a circuit diagram, symbols are used to represent the different types of components that are linked together in a circuit. By understanding what these symbols mean, you can interpret how the circuit is supposed to function. There are 4 components to an electric circuit. Here is the source, like we mentioned before. Your source can be a one cell or multiple cells. Here we have a single cell. And here we have a 3-cell battery. So a cell is drawn like this, with the large end being the positive terminal and the small end being the negative terminal. And these straight lines that I've drawn are the wires. A 3-cell battery would simply be 1, 2, 3 cells together, then connected to a battery. We represent DC power with this symbol here, and AC power with this symbol here. A conductor is drawn as a straight line. These are the wires that connect the components. A light bulb is drawn with a loop surrounded by a circle. A motor, the letter M, surrounded by a circle. A resistor, the zigzag path. And then we have open switches and closed switches. We measure electricity components or quantities using meters. We measure current using an ammeter, potential difference or voltage using a voltmeter, and resistance using an ohm meter. There are 2 ways to connect circuits. You can connect circuits either series or parallel. Let's look at series circuits first. In a series circuit, there is only one path along which electrons can flow. Electrons can easily flow from the negative terminal to the positive terminal. An analogy would be race cars traveling around a single loop track. They only have one path to follow, and they continually travel around that one path. Here are the characteristics of series circuits. Number 1, the current that goes through this circuit is the same in all parts of the circuit. Number 2, if one light bulb burns out in a series circuit, then the current will stop and all the other components of the circuit will stop. You can't just turn off one of the loads. It's all or nothing. So what would happen if we added extra light bulbs in series? Well, since the current that goes through each light bulb in a series circuit is the same, the energy available must be shared between all of the light bulbs. If another light bulb is added, the brightness of the bulbs will decrease. Here's a real example of an electric circuit. We have a battery. Here's the negative terminal, and electrons are flowing through the switch, and then power the light bulb, and power the second light bulb, and return to the battery in a continuous loop around this single path. This is how we draw a circuit diagram for a series circuit with a closed switch, 2 light bulbs, and 1 cell. I'm going to erase this and draw it with you. So let's draw the components. The first thing we'll draw is the cell. This Since there's one cell, we will draw a big line and a small line. This being the plus and this being the minus. From that, I'm going to connect it to a closed switch. This closed switch is going to pass through our first light bulb and our second light bulb, returning back to the positive terminal. And the electrons flow in this direction, from the negative to the positive. Let's try another example together. Let's start with drawing a 2-cell battery. So that's 1 cell, 2 cell. An open switch. An open switch is drawn like this. And 2 light bulbs all connected in series. When you're doing this on a test, I want you to make sure that you use rulers for all of your lines. Now, I could draw the light bulb here, or I can draw it at a different spot. It's still along the same path, so you can draw it in this direction. So we have 1 cell, 2 cell battery, open switch, and 2 light bulbs in series. Now let's take a look at the second type of circuit, a parallel circuit. Parallel circuits are circuits in which there exist 2 or more paths for electrons to flow. It's like cars driving through a large city block, where a car can turn down one street or continue straight and turn down another street. So there's more than one path for the cars to flow through. The good thing about parallel circuits is that if one bulb goes out, the others stay on. As current leaves, it splits into different parts. If the bulbs are identical, the current will split into equal parts. If one bulb has a higher resistance, then less current will go through it. And you can turn off just one light bulb. So what happens if you add another light bulb in parallel? The current separates to go through each branch in the circuit. Energy is not shared in between. Bulbs, therefore, adding another bulb in a parallel circuit would not affect the brightness of the bulbs. Here's a diagram showing 2 light bulbs in parallel. And notice, there are wires connecting this light bulb and this light bulb together. So electrons will leave, travel through the switch, and can either power this light bulb or power this light bulb, and then return back to the positive terminal of the battery. We show a parallel circuit with these junctions. These 2 light bulbs are in parallel with one another. We're going to try to draw our own circuit. This one contains a 3-cell battery. 1, 2, 3. I'm going to label the big side positive and the small side negative. They'll be connected to a closed switch. And 3 resistors in parallel. A resistor is drawn like a zigzag. Here's our first resistor. Our second resistor can be drawn in a separate path in parallel to the first resistor. And the third zigzag parallel path. These 3 resistors are in parallel with one another. Now it says to connect an ammeter after the resistor and a voltmeter across the battery. To draw an ammeter, you have to place it along the path. So I'm going to draw the letter A and put a circle around it. This is an ammeter measuring the resistance or the current flowing through this resistor. When we draw a voltmeter, it's a little bit different. A voltmeter is drawn in parallel. So we have to draw a voltmeter across this battery. In order to do so, we're going to put one wire on one side of the battery and one wire on the other side of the battery. So ammeters are drawn in series and voltmeters are drawn in parallel. Please take the time to complete the practice problems below, as well as any LMS questions that you may have been assigned.